Okay, good morning, lads and ladies. I am excited for today because today we get to learn some cool shit. Today is the day we get exposed to Taylor's Theorem, which is sort of the most general approach we are going to learn in this class for finding a power series. I promised you at the start of this portion of the class on power series that our goal at the end of it was to get to a place where I hand you just about any function and you can come back to me with a power series for that function. Today we learn the thing we need to do that. A few quick notes, comments, test grades are up. I don't remember, I think you guys did not have them ready on Monday. And I don't remember whether I finished your section Tuesday night or last night, but one of those two. So your test grades are certainly up now if they were not up on Wednesday, although I think they were. What else is going on? I don't think there's a whole lot. I do want to say a little something about like academic integrity. That's just please, 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 for the love of fucking God, don't cheat. Right? Do not cheat on my tests. I've been as understanding as I can be because this is, it's online and I get the temptation is there and I want to give you guys opportunities to not necessarily burn your whole academic career over one mistake. And I've also personally gotten to a place of deep frustration where when I see anything that smells cheaty to me, I have this deep temptation to write an angry little comment in there. So I guess a few little notes. If I chastised you saying something kind of looks cheaty, that doesn't mean I'm out to get you, I promise. It just means like, please, whatever this thing is, don't do it in the future. Maybe you didn't show work for a part of something, or maybe there's a step that wasn't entirely justified. Make sure that your work is all there and that every step follows clearly from the previous. And make sure nobody else has access to your shit. Please, like, do not share your work with anybody else, even after you finish the test. I'm not going to be fully militant about it right now. I am trying to get to a place where I can secure academic integrity and keep the value of your degrees safe, while at the same time being compassionate and understanding to the difficulty of the situation you're all in. So if I left you a comment like that, just be aware that on exams 3 and the final, I'm going to be ratcheting up the strictness. And on the final, if I see something that is cheaty and is undeniably cheaty, I certainly will start a conduct trial over that. That would be a shame. And the same will be true on exam 3. So I want to warn you, or not warn you, but apologize perhaps for the tone of some comments I may have left on the test. I'm sorry if you did not cheat and I left you a comment that said this looks suspicious. That doesn't mean I'm out to get you. But it does mean that there's something about that work that made me uncomfortable. And there have been some cases in this class and in other classes where things were undeniably cheating. And in those cases where it's like 100% obvious, I will be going after those people on future tests. So please, please don't do that to yourself. All right, that's all I have to say about that right now. So let's come over here and get started on this really exciting shit we're going to do today. It's a Friday the 13th. That's always fun. Today, we're going to learn about Taylor's theorem. And maybe also do an 11.9 example. So if there are any homework problems from 11.9 that you guys would like to look at that have been driving you absolutely apeshit crazy, just can't get it right, or something just feels weird, I'd actually like to begin today with one of those examples. So are there any problems from the homework 10 or the first half of homework 11 that you guys would like to take a look at? Anything you've been working hard on, but you feel like you need a little bit of help with? This is if desired. So if so, please let me know in chat here, homework 10, problem 6, something, whatever.
I have one, I just can't remember the number. I'm trying to find it right now.
Okay, I do believe I have homework 10 handy. You can look at homework 11 here. I can scroll through it. We haven't covered everything from this yet. So number 1 in homework 11 was where you differentiate to find a series. Number 2, we actually did this last week. Natural log of 5 minus x.
It was number 3, yeah.
Number 3 here. Okay, we can take a look at this. So we want to find the power series for x squared times the inverse tangent of x cubed. I should say f of x equals x squared times the inverse tangent of x cubed. All right, well, the place we're going to begin here is with the series for the inverse tangent of x that I gave you guys last time. And maybe even two classes ago. Does anybody remember that all-important power series for the inverse tangent of x that I said we need to remember forever and ever along with its IOC? We put it in a blue box.
-1 to the n times x to the n.
Little bit more going on there. So there's a sum to infinity, and there is going to be a -1 to the n, but what else?
Over 2n plus 1 times x to the 2n plus 1.
Yeah, good. Okay, so I'll write that like this. -1 to the n times 1 over 2n plus 1 times x to the 2n plus 1. Okay. So that's the power series for inverse tangent of x. What I need to get started here, this is x squared times the inverse tangent of, not x, but x cubed. So I can start with a series for this. How could I get a series for this when all I have is a series for this? Well, everywhere in here, really just here, I can swap in an x cubed for the x. But everything else will come along for the ride. You guys see that trick? That's a sneaky little trick. If arctan of x is this, then arctan of x cubed is this. Just everywhere there is an x here, I write an x cubed. That's just the one spot here. And then I can clean this up. X cubed to the 2n plus 1 is x to the 3 times 2n plus 1 like this. So this is sigma n from 0 to infinity, -1 to the n over 2n plus 1 times x to the 6n plus 3. That's the series for the arctan of x cubed. Therefore, x squared times arctan of x cubed is equal to x squared times this series. And then you can bring the x squared inside. x squared times x to the 6n plus 3, you just add the powers. 6n plus 3 plus 2 is 6n plus 5. That's your power series. And then define the interval of convergence and the radius of convergence, all the good shit. You would run the ratio test on this. Right, just like you do for all the power series back in 11.8. Run the ratio test, check the endpoints. That will give you your interval of convergence, from which you can deduce the radius of convergence. Do we want to see the IOC work done out here? Or are we comfy leaving it at this? I'll leave it up to you guys.
You had time to go over another problem.
Yeah, I could do a different problem instead.
Same homework, number 5.
Sure, yeah, this is a fun one. Let's log 1 plus x over 1 minus x. So same game. Oops, sorry about that. I'll get that out of the way. So we want to find a series for f of x equals ln 1 plus x over 1 minus x, right? Do you guys remember when we did, oh, this is homework 10, isn't it? Is this 11 or 10? Oh no, it's 11, okay. So do you guys remember when we did number 2? When we did this one last week, or it was Monday, when we did this one on Monday? You remember what our first step was here? We factored out a 5 inside the log and then used properties of logarithms to expand. Well, here my first step is going to be to write this as ln of 1 plus x minus ln of 1 minus x. And then I'm going to find a power series for each of those two things, and then I'll put them together. So we'll find a series for each of these.
We know the power series for ln of 1 plus x, right?
Yes, very good. What is the power series for ln of 1 plus x?
Series from 0 to infinity, negative 1 to the n over n plus 1, x n plus 1.
Good. And we can deduce from that the series for ln 1 minus x. Think about what we did in the arctan problem. This is the same as the ln of 1 plus negative x. So I can swap a negative x in here, right? 1 plus whatever has this series. 1 plus negative x. Okay, just swap the x for a negative x. But before I go any further, I would like to simplify this before I start trying to glue these together. Negative x to the n plus 1 is negative 1 to the n plus 1 times x to the n plus 1. Because negative x is negative 1 times x. And now I've got this negative 1 to the n and this negative 1 to the n plus 1. Well, negative 1 to the n times negative 1 to the n plus 1 is negative 1 to the 2n plus 1. You just add the powers. Well, shit, 2n plus 1 is always odd, so that's just negative 1. So this is negative sigma n from 0 to infinity, positive 1 over n plus 1 times x to the n plus 1. With the two powers of negative 1 combining to just make negative 1. Is everybody with me so far? This times this is just negative 1, because 2n plus 1 is always odd. So when I put these two together, I get just a regular old negative 1, which can come outside the series, because it's a constant. Now we're ready to solve the problem. My function, which is the natural log of 1 plus x minus the natural log of 1 minus x, must be the series for the natural log of 1 plus x, sigma n from 0 to infinity, negative 1 to the n over n plus 1 times x to the n plus 1. I'll put that in parens because that's the first piece. Minus this minus is this minus. And then the series for the second piece, which is negative sigma n from 0 to infinity, positive 1 over n plus 1 times x to the n plus 1. Now remember, the rules for capital sigma are the same as the rules for integrals. So first, maybe I'll write this like this. Sigma n from 0 to infinity, negative 1 to the n over n plus 1, x to the n plus 1. Minus minus here makes plus. So if I have the integral from 0 to infinity of f of x plus the integral from 0 to infinity of g of x, that's the same as the integral from 0 to infinity f of x plus g of x. So here I can write this as the sum from 0 to infinity, negative 1 to the n over n plus 1 times x to the n plus 1 plus 1 over n plus 1 x to the n plus 1, like this. I can put these two sums together into a single sum because they're both being summed from 0 to infinity. The stuff from the first series goes right here. The stuff from the second series goes right here. And I've just combined the two sigmas into a single sigma. You can kind of think of it like factoring out the sigma on the left. It works that way.
Do we have to work it out that far or?
Oh yeah.
Okay.
No, we're not done yet. Yeah, we're still not to a place where we're happy with this.
Okay.
This is coming from the fact that sigma of an plus bn is the same as sigma an plus sigma bn, as long as everybody's convergent. But this is still not a power series down here. Remember, a power series needs to be some coefficients times a power of x. So I've got x's showing up in multiple places here. I'm not happy with that. But you can factor the x to the n plus 1 out on the right, and along with it, you can bring the 1 over n plus 1. So here's what I'm going to do. Factor out the 1 over n plus 1 times x to the n plus 1. What's going to be left over here is negative 1 to the n plus 1. And this you could hand it. This would be an acceptable answer to the problem. But it's still not nice. And it can be written nicely. So while this I would give credit for, if you had to then go on and do some other shit like integrate this or differentiate this, you really don't want to leave it like that. It is not a very workable form. So let me acquire some free space here. Let's write out the first few terms of this. If I plug in n equals 0 here, I get -1 to the 0 plus 1. That's 1 plus 1, that's 2. 2 times 1 over 0 plus 1, that's 1 times x to the 1. When I plug in n equals 1, I get -1 to the 1 plus 1. That's 0, that's -1 plus 1. And then I'd have 1/2 and x squared. When I plug in n equals 2, I get -1 to the 2 plus 1. Oh, well, that's 2 times 1 over 2 plus 1. That's 1/3 times x to the 3. The next term would be 0 times 1/4 x to the 4, and then 2 times 1/5 x to the 5, and so on. Now, if I stop writing the zeros, that's 2 times x plus 2 times 1/3 x cubed plus 2 times 1/5 x to the 5. What would the next term be here?
Two times 1/7 x to
Good, very good. So now if you wanted to, if I just gave you this and I said, write it in sigma notation, you could call that the sum from 0 to infinity, 2 times 1 over 2n plus 1 times x to the 2n plus 1. The 2 is just a 2. It's coming from these 2's. The 2n plus 1 stuff, that's how you get odd numbers, right? 2 times 0 plus 1 is 1. 2 times 1 plus 1 is 3. 2 times 2 plus 1 is 5. 2 times 3 plus 1 is 7. This, I think we'll all agree, is a much nicer thing than this, if you got to work with it. For example, if you had to differentiate it or integrate it. So I would argue that the good answer to this question is this thing. Although this is also acceptable. But this is ugly. This is very pretty. This is easy to work with. This is hard to work with. One thing from this, I can see immediately, remember our discussion last week, that this is an odd function because its power series contains only odd powers of x. Here, totally opaque. Cannot tell whether that is an even function or an odd function. This, if I wanted to differentiate, I could differentiate very easily, and it's easy to see what the derivative would be. This, if I want to differentiate, it's going to be a little bit ugly because it's still going to have this fucking thing here. So this is a nice solution to problem 5. And then if you wanted to find the interval of convergence, you'd run the ratio test. Questions on this? Okay. Let's talk about Taylor's theorem then. So we're ready. Taylor's theorem says this: if f of x can be written as a power series centered at A, meaning can be expressed as sigma n from 0 to infinity Cn times x minus a to the n, then Cn is Fn of a over n factorial, i.e., or that is, any function f of x can be written as sigma n from 0 to infinity Fn of a over n factorial times x minus a to the n. I know this looks scary. Here, let me de-scare it for you. Fn of a is the nth derivative of f of x evaluated at x equals a. So this notation with the parentheses, n here, looking like a superscript, looking like a power, stands for the nth derivative. So f0 of x is f of x, differentiate 0 times. f1 of x is f primed. f2 of x is f double primed. It's just that we're going to use many higher derivatives like third, fourth, fifth, sixth derivative. And you don't want to write 6 primes, it looks silly. I'm going to prove this theorem for you. Proof. We're going to write f of x as this series, which is c0 plus c1 times x minus a plus c2 times x minus a squared plus c3 times x minus a cubed plus, I'm so sorry, I can't help this, c4, the dangerous coefficient, times x minus a to the 4, and so on. My Calc 2 professor could not stop making jokes about c4, and it's stuck in my head for the million years since then. All right, what we're going to do, we will show that the CNs are what we said they would be. You ready? All right, step 0. Just plug in the center. F of a would be c0 plus c1 times a minus a plus c2 times a minus a squared plus blah, blah, blah. All of these are 0. So f of a is c0, or c0 is f of a divided by 0 factorial. Sure, because 0 factorial is 1. 1. Differentiate f of x. So I'm going to differentiate here. C0 will differentiate to 0 because it's a constant, plus C1 times x minus a. C1 comes along for the ride. The derivative of x minus a is 1, plus the derivative of c2 times x minus a squared is c2 times 2 times x minus a to the 1, plus the derivative of c3 times x minus a cubed is c3 times 3 times x minus a squared. This is a 2. Plus the derivative of c4 times x minus a to the 4 is c4 times 4 times x minus a cubed. And it goes on and on like this. Same thing, plug in A. So f primed of A is 0 plus C1 times 1 plus C2 times, no, shit, C2 times 2 times A minus A to the 1 plus C3 times 3 times A minus A squared plus C4 times 4 times A minus A cubed, and so on. And just like before, this is 0. This is 0. This is 0. So f primed of A is C1. Times 1 if you want. So C1 is f primed of A. And you can say it's divided by 1 factorial if you want to, because who gives a shit? It's just 1 factorial is 1. If I differentiate the original series at the very top twice, if I differentiate this series twice, that means I'm taking the derivative of this thing, because this is the first derivative. So let's differentiate this. 0 differentiates to 0. C1 times 1 differentiates to 0. C2 times 2 times x minus a to the 1, well, that differentiates to 1. So that's C2 times 2 times 1 plus C3 times 3. The derivative of x minus a squared is 2 times x minus a to the 1 plus C4 times 4. The derivative of x minus a cubed is 3 times x minus a squared. I'm going to go ahead and write what the next term would be here. The next term would be C5 times 5 times 4 times x minus a cubed. And it would go on and on like this. Now plug in A. All of these are 0, right? When we plug in A, sorry, I won't write them like that. That's misleading. But all of these next terms would be 0, yeah? C3 times 3 times 2. If you plug in A here, you get A minus A. You plug in A here, you get A minus A. You plug in A here, you get A minus A. So C2 is f double primed of A over 2. And 2 is the same as 2 factorial, right? 2 times 1. We can do this as many times as we want. I will do 2 more for you. If I differentiate one more again, f triple primed of x, this piece will differentiate to 0 because it's a constant. This piece will differentiate to C3 times 3 times 2 times 1. This piece will differentiate to C4 times 4 times 3 times 2 times x minus a to the 1. This piece will differentiate to C5 times 5 times 4 times 3 times x minus a squared. And it goes on like that. So if you plug in A, f triple primed of A, all of these go to 0. You just get C3 times 3 times 2 times 1. In other words, C3 is f triple primed of A divided by 3 factorial. One more again, and then we're going to call it a day. If I differentiate this expression, that will give me, and I'm not going to write 4 primes, I'm going to write it as f4 of x, because that's what the parentheses notation here means. This is the 4th derivative. It's the derivative of f triple primed. This piece is a constant, so it will differentiate to 0. This piece will differentiate to C4 times 4 times 3 times 2 times 1, because the derivative of x minus a to the 1 is just 1. Plus, this piece will differentiate to C5 times 5 times 4 times 3 times 2 times x minus a to the 1. The next piece would look like C6 times 6 times 5 times 4, 1, 2, 3, 4, times 3 times x minus a squared, and so on. So F4 of A is C4 times 4 times 3 times 2 times 1. In other words, C4 is the fourth derivative of F evaluated at A over 4 factorial. Now look at these coefficients that we found. Those do indeed fit the pattern claimed by the theorem, don't they? Cn is always the nth derivative of f evaluated at the center divided by n factorial. So the theorem is true. That's it. If you differentiate the series n times, all the terms up to the nth one will disappear because they were of degree less than n. You differentiate something like x cubed or x to the 4 5 or 6 times, they'll differentiate to 0. And the first non-zero term will be n factorial times Cn. So when you plug in the center, all the higher order terms go away, and you just get that the nth derivative of your function evaluated at the center is equal to the nth coefficient times n factorial. Now, as always, you're responsible not for the proof of the theorem, but for the use of the theorem. So here's the theorem. How do we use it? Well, somebody hands you a function f of x. You want the power series. The only thing you need to figure out the power series is the coefficients and the center. So somebody hands you a function, you pick a center, or maybe they tell you the center that they want you to use. Either way, that sorts out A. Then you need to come up with the CNs. This is the formula for the CNs. There's a catch here. The catch is you need to figure out the nth derivative of your function evaluated at the center. That's not always easy, is it? I can differentiate once or twice, 3, 4, 5 times, but here you need a formula for the nth derivative. So this can get a little tricky. I'd like to show you a few simple examples, or at least one simple example, and then a more challenging one. Let's say find, oh, and a bit of language here. We're going to find the Taylor series for f of x equals e to the x centered at a equals 0. A quick note. A power series or Taylor series that is centered at a equals 0 is called a Maclaurin series. right? So anytime you have a series centered at 0, Maclaurin, that's called a Maclaurin series. Maclaurin series is the same thing as a Taylor series or a power series, just with the center being 0. So if A is 0, we call that a Maclaurin series. You'll see that vocabulary in your homework. Sometimes instead of saying find the power series for this centered here, they just say find the Maclaurin series. Find the Maclaurin series means find the power series centered at 0. Here's how I like to do this. You make a table. When n is 0, the 0th derivative of my function is just my function. That's e to the x. Then you plug in your center, whatever your center is. Here, my center is 0. So f0 of 0, well, that's e to the 0, that's 1. So c0 is 1 over 0 factorial. Remember, Cn is Fn of the center over n factorial. When n is 1, F1 of x, that's the first derivative, or f primed of x. Well, the first derivative of e to the x is still e to the x. So f1 of 0, that's still e to the 0, that's still 1. Which means that c1 is 1 over 1 factorial. Nothing terribly exciting there. When n is 2, f2 of x, that's f double primed. That's the second derivative. Well, shit, that's still e to the x. So f2 evaluated at the center, remember here the center is 0. In general, you would plug in whatever your center is. Well, that's still e to the 0. So that's still 1. So c2 is 1 over 2 factorial. Does anybody see a pattern? What is the nth derivative of my function? I differentiate 0 times, I get e to the x. I differentiate once, I get e to the x. I differentiate twice, I get e to the x. I differentiate n times, what am I going to get?
E to the x.
Good. So if I differentiate n times and then plug in 0, that means I'm just going to plug in 0 to this. That's still going to be e to the 0. So Fn of my center is still 1. Which means that Cn in general is this divided by n factorial. That's 1 divided by n factorial. This is what one of these tables looks like when they are complete. You calculate as many rows as you need in order to spot the pattern. Once you have spotted the pattern, you fill out the nth row of the table. The thing all the way over here is what you're after. Remember what we said, we just need the CNs. If you know A and the CNs, then you know the series. Therefore, remember f of x is always sigma n from 0 to infinity Cn times x minus a to the n. Well, here f of x is e to the x. Sigma n from 0 to infinity. Cn is 1 over n factorial. And the center I'm using here is 0. So x minus a to the n is just x to the n. This is the most important power series in all the land. This is the power series for e to the x. The interval of convergence here, you may remember, you've actually seen this series before. This was in a homework problem from 11.8. The IOC here is negative infinity to infinity. You just didn't know back then that that was the series for e to the x. Everybody along with me here? E to the x is the easiest possible example because no matter how many times you differentiate it, it stays e to the x. Most of the time, the hard work will be in this column. What you write here is what you get here in the second column, and then you plug in the center. Sometimes you'll want to do some simplification here. In this problem, it was easy. They were all just 1. So the CNs were all just 1 divided by n factorial. That wasn't hard. But in general, these will look more complicated. And I'll show you some examples where these are more complicated. But first, I just want to get you comfortable. So are we comfortable with what we did in this table and how we used it to write down this series? Are there any questions we'd like to ask about these things? Where did this come from? Where did that go? Why did we write it that way? Okay, then. I am going to do a few things before I show you another explicit example. Some notation. If f of x has this power series, n from 0 to infinity, Cn x minus a to the n, that's the same as sigma n from 0 to infinity, fn of a over n factorial times x minus a to the n. If this has a Taylor series like that, then we call the partial sums they're called Taylor polynomials. T0 of x is just f of a. You plug in n equals 0 here, you get f0 of a divided by 0 factorial times x minus a to the 0. The next partial sum is f of a plus f primed of a times x minus a. Then the next partial sum is f of a plus f primed of a times x minus a plus f double primed of a over 2 times x minus a squared, and so on. T3, the last one I'll write here, f of a plus primed of a times x minus a plus f prime primed a over 2 times x minus a squared. The next term is the third derivative evaluated at a over 3 factorial times x minus a cubed. The partial sums of a Taylor series are called Taylor polynomials. And instead of calling them S0, S1, S2, we call them T0, T1, T2. And we put the x here to remind us that they are functions of x. Anybody recognize this sumbitch? What is this thing? Think back to Calc 1. Where have you seen that formula before in Calc 1? It was before you started talking about integrals, but after you learned about the chain rule. Actually, you saw it before the chain rule too. It's the linearization of f. In other words, the tangent line. This is the tangent line. At x equals a. So I want to show you the partial sums for that power series we just cooked up. E to the x, we just said, has power series sigma n from 0 to infinity 1 over n factorial times x to the n. That's an explicit example. So T0 is just 1. T1 is 1 plus x. T2 is 1 plus x squared over 2. T3 is 1 plus x squared over 2 plus x cubed over 3 factorial is 6. Let's look at what these Taylor polynomials look like. I am going to flip to Desmos in about 5 seconds. Oh shit, they're already here. All right. Okay. So forget about the y equals, right? I'm just saying that so I can get the graph. Here's T0, right? The red is e to the x. The blue is T0. Here's T1. Like I said, that's the tangent line. The first order Taylor polynomial, T1, is the tangent line to f of x at the center. So this series is centered at 0. So this is the tangent line to a to the x at 0, as claimed. T2 is the tangent parabola. This is the second order version of the tangent line. It goes through the point 0, 1. It has the same derivative as the red function at 0, and it has the same second derivative. The curvature also matches. T3 is the tangent cubic function. It goes through that point. it has the same first, second, and third derivatives as e to the x at that point. T4 looks like this. So here you can see the partial sums of the Taylor series converging to the function, the blue getting closer and closer to the red. And the more terms I use, the better it will be. There's T5, here's T6. And you can see that T6 does a better job sticking close to the red than the blue did. All right, there's T5, there's T6. T6 sticks close to the red a little better than T5 does. The vertical gap, look just at -2 here. The vertical gap between the red function and the green function is smaller than the vertical gap between the red function and the blue function. Bigger gap, smaller gap. This is what it looks like for a Taylor series to be converging to a particular function. These are the partial sums of that Taylor series. You can find this animated in some places. Here they will show the Taylor series for sine. Getting closer and closer and closer to matching the original function. The colored graphs that you're seeing here are Taylor polynomials. The black graph is sine x. So the next thing I would like to do for you is cook up this polynomial, cook up this Taylor series for sine. Any questions on the notation here, what these symbols mean, or how I'm getting T3 as this? All right, I'm just taking the first n terms for Tn. Here, when n is 0, I get 1 over 0 factorial times x to the 0. When n is 1, 1 over 1 factorial times x to the 1. When n is 2, 1 over 2 factorial times x to the 2. When n is 3, 1 over 3 factorial times x to the 3. When n is 4, it's 1 over 4 factorial times x to the 4, and so on. So these really are just the partial sums of this series. Since this series has powers of x in it, the partial sums are polynomials, and we call them Taylor polynomials. So I would call this the degree 3 Taylor polynomial for e to the x centered at a equals 0. Okay. I'm going to do one more explicit example for you, and then I'll let you go. You guys are a little bit ahead of my other class. And I would like to keep you close together. That makes my life much easier. And it keeps you from getting overwhelmed. One more again. This one's going to be a little trickier. Let's find the Maclaurin series for f of x equals sine x. Remember what Maclaurin series means. What does this mean?
It's centered at 0.
Good. So I'm going to build my table. N, Fn of x, Fn of a, and here a is 0, so I'll just go ahead and put that in. And then Cn, which is Fn of 0 over n factorial. You'll find that most of the time we center these at 0, but not always. Here I'm going to need quite a few terms to recognize the pattern. When n is 0, f0 of x, if I differentiate 0 times, I just get sine x. If I plug in my center, f0 of 0, that's the sine of 0. What's the sine of 0?
0.
Bueno. So C0 is 0 over 0 factorial. That's 0 over 1. That's 0. When n is equal to 1, the first derivative of my function, what's the derivative of sine?
Cosine.
So that's cos x. And the first derivative evaluated at 0, that's going to be cosine of 0. What's that?
1.
So C1 is 1 over 1 factorial, which is 1 over 1, which is 1. When n is 2, f2 of x, the second derivative of sine, or the derivative of cosine, is what?
Negative sign.
Good. And if I plug 0 in for x, f2 of 0 is negative sine of 0. That's 0 again. So C2 is 0 over 2 factorial, which is 0 over 2, which is 0. When n is 3, f3 of x is the derivative of negative sine. What's that?
Negative cosine.
Good. Negative cos x. So f3 of 0 is negative cos of 0, which is negative 1. So C3 is negative 1 over 3 factorial. And I'll just leave it as that, honestly. I'm going to need a few more terms here before I start to notice a pattern. When n is 4, f4 of x, the derivative of negative cosine is positive sine. When you plug in 0, f4 of 0 is the sine of 0, which is 0. So C4 is 0 over 4 factorial, which is 0. When n is 5, f5 of x, if I differentiate sine, I'll get cosine. So f5 of 0 is the cos of 0, which is 1. So C5 is 1 over 5 factorial. F6, the derivative of cos is negative sine. F6 of 0 is negative sine of 0, which is 0. So C6 is 0 over 6 factorial, which is 0. All right, last one. When n is 7, f7 of x, the seventh derivative of sine, is the derivative of negative sine x, which is negative cos x. So f7 of 0 is negative cos of 0, which is negative 1. So C7 is negative 1 over 7 factorial. All right, what pattern do we see? C0 is 0. C2 is 0. C4 is 0. C6 is 0.
Every other number is 0.
Yeah, Cn equals 0 if n is even. Now here, you're not going to be able to find a nice formula for the Cn's. If n is even, then Cn is 0. And if n is odd, then it alternates between positive and negative and positive and negative. And you also have the 1 over n factorial shit going on. So let's write this out. Sine of x is c0 plus c1x plus c2x squared plus c3x cubed plus c4x to the 4 plus c5x to the 5 plus c6x to the 6 plus c7x to the 7 plus c8x to the 8 plus c9x to the 9 and so on. All the evens are 0. So this is 0 plus, what was C1? It was 1. Plus 0, x squared is 0. And then C3 was minus 1 over 3 factorial. Plus C4 was 0. C5 was plus 1 over 5 factorial. So it's 1 over 5 factorial x to the 5. Plus C6 was 0. C7 was minus 1 over 7 factorial. So it's this. Plus C8 is going to be 0. What's C9 going to be?
One over factorial 9 times x to the 9.
Good. Yeah, C9 is positive 1 over 9 factorial. So this term would be 1 over 9 factorial x to the 9. Let's write this without the zeros. That's x minus 1 over 3 factorial times x cubed plus 1 over 5 factorial times x to the 5 minus 1 over 7 factorial times x to the 7 plus 1 over 9 factorial times x to the 9. What would the next term be?
One over factorial 11 times x to the 11.
Good. And it would actually be negative, right? Because they're changing sign. Minus 1 over 11 factorial times x to the 11. This I can now put into sigma notation. This is sigma n from 0 to infinity. It's alternating. Downstairs, I have odd numbers factorialed, and upstairs, I have just x to those same odd numbers. This is the power series for sine x. This is the Maclaurin series for sine x. After your series for e to the x, this is the most important power series. And you need to remember this guy. His IOC is also negative infinity to infinity, but you should work that out yourself. Don't just take my word for it. So you can see what we're doing. We're building up a library of known power series, right? 1 over 1 minus r, your geometric shit, arctan and natural log from last week, e to the x and sine of x here. My next move, although I'm not going to do it today, would be to get a power series for cosine. The long way to do that is to run back through all this shit, but for cosine. Can anybody think of a smarter way to do it? Given what we have right here.
Shouldn't it just be all the evens?
Well, yeah, but I mean, how do you know that? Let me ask that a different way. Is there a direct way to get a power series for cosine from this rather than rebuilding a table? If you have a series for sine, how do you get a series for cosine from that?
Can you make the bounds from n equals 1 to infinity?
Easier. That wouldn't quite work, no.
You just take its derivative.
Fuck yes. Differentiate this thing. This is sine. If you differentiate it, you're going to get cosine, right? So if you differentiate this series, you'll get a series for cosine. I will do that for you guys next Monday. Now, because we ended up losing a lot of time this week, we lost Wednesday to the holiday and we lost Thursday office hours to the hurricane, I'm going to extend the current homework. Although you do technically have, I believe, everything you need to finish it. Here is the current homework. I don't believe there's anything in here that you are unequipped to do, but I would like to spend a little bit more time working with and talking with you guys before I hold you responsible for doing this on your own. Now, definitely, we have covered everything you need to solve all the way up through problems 15 and 16. So I would like you guys by Monday to have finished homework 11 up through problem 16. And even though you have everything you need to do the rest of these, I want to spend a little bit more time talking and working with you guys before I hold you responsible for it. So please work hard on this homework. Try to get all the problems up through number 16 done by Monday, and we will talk more about this stuff on Monday next week. All right? Questions for me before we depart? Okay then, I hope you guys have a lovely rest of your day. Please work hard on that homework, review your exams. The exam scores and comments are all in. If you took the exam at an odd time or you didn't send me your written work through Canvas, I'll be grading those over the weekend. They still need to be done. Also, I had to do a bunch of stuff for another class. So I know I said I'd try to have your study guides done by Thursday. That clearly didn't happen. I'll need just a little bit more time on that. But over the weekend, I'll be going back and cleaning up any grading that still needs to be done. So if you sent me your work through some other channel or you took the test on a weird day, then I'll get those in over the weekend along with the study guides. All right. If you do have questions for me, please come see me in office hours or send me an email, Canvas message, that sort of thing. That is it from me. I hope you guys have a lovely rest of your day and enjoy the weekend, and I'll see you on Monday.